Hi everybody. I want to show you how to do a randomization test for proportions. And what that essentially means for us here is that we've got two groups that we want to compare, and the outcome that we're measuring for the individuals in each group is a binary variable, which will lead us to proportions, and we want to learn how to compare them. Because we're learning how to do a significance test, we want to remind you of the 5 essential steps that outline how the process works. We have to start with a question. What is it that we want to learn about? We need to translate that question into hypotheses, and these will have a special form because it's a 2-sample test. Then we need to gather and summarize data in order to learn whether we should reject or fail to reject that null hypothesis that we write. The evidence we'll get will be in the form of a p-value, and that will tell us what to do, although how we get the p-value in this situation is a little bit different. And then we'll interpret that p-value in order to tell us what kinds of conclusions should we draw with respect to our hypotheses, and in the end we'd really like to be able to answer the question that we stated to begin with. So let's do this through a particular example. This one has to do with the question, do people spend differently when they have different currency denominations? I know I've experienced that if I've got a $20 bill, or if I've broken that $20 bill down into, maybe it's even a 10, a 5, and 5 ones, I feel like I'm much more likely to spend the $20 once it's broken down into smaller denominations. The $20 bill I want to keep whole. Well, these researchers decided to test this in a variety of ways, and one of the ways they did was they got some people, and they split them into 2 groups. In one of the groups they gave a dollar bill, and in the other group they gave people 4 quarters. And then they asked them whether they wanted to keep the money that they'd been given, or whether they'd like to take the opportunity to buy some gum or mints. So just to be clear, an individual would then be one participant, and the explanatory variable is which group they got in. Did they get the dollar or did they get the quarters? And that's a binary variable. And the response variable is whether they chose to spend or keep the money, also a binary variable. Notice that this is an experimental condition because they've randomized the individuals into 2 groups. So here's the question we want to answer, and we're translating it first into a null hypothesis. Pi sub q equals pi sub d, meaning the proportions are the same in the groups of people that are being represented by the samples. And the alternative hypothesis is that those proportions are not equal, and we've chosen a 2-sided hypothesis. In words, we're only going to write the null hypothesis. We'll just state the null hypothesis in words. This is that there is no association. In other words, the proportions of people who are going to hang on to the money would be the same in either group, no matter whether they got the dollars or the quarters. So next thing we need is we need to gather and summarize some data. So here is a 2-way table that shows us the results. There were 46 people in one group, 43 in another group. Remember that they were randomly assigned, and we need to calculate the sample proportions. So in the group that was given the dollar bill, group 1, 12 out of the total 46 is 26.1%, and in the other group we notice 62.8%. Seems like kind of a big difference, and in fact we need to calculate the difference. It's a 36.7 percentage point difference between the 2 groups. It seems like a big difference, but remember we have to rule out sampling variability as perhaps being what might be the cause of that difference. This 0.367, the difference in the 2 sample proportions, is what's called a test statistic, and this is the number that we use in order to test to see whether could such a difference have occurred by chance alone. So the next step is to get that p-value, and so we're off to the randomization test. The randomization test occurs inside of StatKey. I need to choose a randomization test for a difference in proportions. So we'll get it set up, and then I'll explain to you how it works. So in the edit data, in group 1, I usually like to put the group with the higher percentage first, but it really doesn't matter in the end. 27 out of 43, and then 12 out of 46 in the other group. And when I push OK, what's going on now? And we can check over here to make sure that we've entered the data properly with the right percentages. And notice that StatKey even shows us what the difference in percentages is with this 0.367. So remember that the individuals were randomly assigned to the 2 groups. And what we're trying to find out now is whether the randomization itself is what might be responsible for a difference as large as 36.7%, or whether there's something else going on. In fact, maybe it is that the difference in treatments is responsible for a difference of 36.7%. When I generate one sample, that's one random reshuffling, re-randomization of the individuals, and let's see if the difference turned out to be the same. No, this time it's only actually less than 1/10 of 1%, much more balanced. When I generate one sample again, the difference is about 4%. When I do it again, 17%, this time 8%. Each time I do it, I'm getting something a little bit different, and that's because of the randomness that's involved. But what I'm trying to learn is whether a difference of 36.7% is consistent with the null hypothesis. If it is, it should pop up a fair number of times. So what I've got to do is I've got to generate several thousand samples, and we usually like to have a minimum of 5,000. So there we go. Now, even a quick look shows us that something at least as extreme as a difference of 36.7% didn't occur very often. But we'd like to be more specific and count exactly how many times did that happen in our 5006 randomizations. Because the difference is positive, we want to change the cutoff bubble on the positive side of the axis. So here's where we'll enter the 0.367 so we can learn how often did a randomization occur that was at least as extreme as the one in our sample. This is where we get our p-value. We add the number on the right, the 0.0004, to the number on the left, 0.0004, and that will give us the p-value. So like I said, we add those two numbers together and we get a p-value of 0.0008 from the randomization test, and now we need to interpret what is it that this tells us. Well, for a p-value that small, we reject the null hypothesis because we have very strong evidence against it. We have found a statistically significant difference between the proportions in the two groups. And in our new language, what we're saying is that the treatment, that is whether they got quarters or a dollar bill, and the spending, whether they chose to spend or not, those two variables are associated with each other. When we change the explanatory variable, there is a corresponding change, the response variable. Not for every single individual, but enough that we're noticing some sort of trend. And finally, we want to say something in plain language that relates back to the question. And what we might say is that in this experiment, the spending did tend to change depending on whether the individuals were given quarters or dollars. They seemed much more likely to spend the money if they were given quarters than they were if they had dollars. That's all for now. We'll reference this example again in a future video, but for now, if you have any questions, let me know.